So use a smaller step size. And the picture roughly which is going to justify that will look like this. If the solution curve looks like this, then with a big step size, I'm liable to have something that looks like that. But if I take a smaller step size, suppose I have the step size, how is it going to look then? Well, I better switch to a different color. If I have the step size, I'll get a littler. It goes like that, and now it's following closer. Of course, I'm stacking the deck, but see how close it follows? You know, I'm definitely not to be trusted on this, but there. Okay, let's do the opposite, make a really big step. Suppose instead of the yellow one, I'd used the green one. Well, a double step size. Well, what would have happened then? Well, I've started out, but now I've gone all the way to there. And now on my way up, of course, it has a little further to go. But if for some reason I had stopped there, you could see I would be still lower. In other words, the bigger the step size, the more the error. And where are the errors that we're talking about? Well, the way to think of the error is this is the error. That number, the error, and you can make it a positive, negative, or just put automatically an absolute value sign around it. That's not so important. So in other words, the conclusion is that the error E, the difference between the true value that I should have gotten and the Euler value that the calculation produced, the error E depends on the step size. Now, how does it depend on the step size? Well, it's impossible to give an exact formula, but there's an approximate answer which is, by and large, true. And the answer is, so E is going to be a function of H. What function? Well, asymptotically, which means is another way of putting quotation marks around what I say. It's going to be a constant, some constant, times H.
Don't be late. It's you, pretty boy.
Nobody knows. Take care. It looks like this, and for this reason, it's called a first order. The Euler is a first order method. And now, first order does not refer to the first order of the differential equation. It's not that use of the word first. It's not the first order because it's y prime equals f of x, y. The first order means the fact that h occurs to the first power. The way people usually say this is, since the normal way of decreasing the step size, as you'll see as soon as you try to use the computer visual that deals with the Euler method, which I highly recommend, by the way, so highly recommend it that you have to do it, is that the way to say it, that since you each new step halves the step size, that's the usual way to do it. If you have the step size, since this is a constant, if I have the step size, I have the error, approximately. Have the step size, have the error. That tells you how the error varies with step size for Euler's method. Please understand, that's what people say, and please understand the grammatical construction. Since everyone in the math department has a cold these days, except me for the moment, everyone goes around chanting this mantra. This is totally irrelevant. So mantra, feed a cold, starve a fever. And if you ask them what it means, they say it means, eat a lot if you have a cold, and if you have a fever, don't eat very much. Which is not what it means at all. Grammatically, it's exactly the same construction as this. What this means is, if you have the step size, you will have the error. And that's what feed a cold, starve a fever means. And remember this for the rest of your life. If you feed a cold, if you eat too much when you have a cold, you will get a fever and end up having to starve yourself, because, of course, when you have a fever, nobody feels like eating, so they don't eat anything. All right? You got that? You got that. Good. Good. Go home. I want all of you to go home and tell that to your mothers. That's the way we always used to speak back, a grimmer one, spare the rod and spoil the child, does not mean that you should not hit your kid. And it means that if you fail to hit your kid, he or she will be spoiled, whatever that means. So you don't want to do with that. I guess the mantra today would be I don't know. Okay, so the first line of defense is simply to keep having the step size in Euler. And what people do is, if they don't want to use anything better than Euler's method, is you keep having the step size until the curve doesn't seem to change anymore. And then you say, well, that must be the solution. And I ask you on the problem set, how much would you continue to have the step size in order for that good thing to happen? However, there are more efficient methods which gets the result faster. And so, if that's our good method, let's call this a still better method. The better methods aim at being better. They keep the same idea as Euler's method, but they say, look, let's try to improve that slope an. In other words, since the slope an that we start with is guaranteed to be wrong if the curve is convex or concave, can we somehow correct it so that, for example, instead of immediately aiming there, can't we somehow aim it so that by luck the next step just lands us back on the curve again? In other words, we're sort of looking for the short path, a shortcut path, which by good luck will end us up back on the curve again. And all the improvements, the simple improvements on Euler method, and they are the most stable in ways to solve differential equations numerically, aim at finding a better slope. So they find a better value for a better slope, find a better value for than an. Try to improve that slope that you found. Now, once you have the idea that you should look for a better slope, it's not very difficult to see what, in fact, you should try. Again, I think most of you would say, hey, I would have thought of that. And you'd be closer in time, since these methods were only found about maybe 100, around the turn of the last century is when I placed them.